and 1, provided that the variables are transformed in accordance with equation 3. Here the numbers of equations are without the addition that it's for 2.4 chapter. So this equation are working inside this chapter. And one more task. Carry out detailed transformation to obtain the system of 3-scalar equation 9 from the first vector equation of the geostrophic system 8. This is the second task. And actually, when I spoke to you, I also formulated the task, maybe even 2 tasks. Okay. Please explain in the detail how you got the equation 12 from the previous equations. And also the similar problem. Please explain in the detail how you got equation 14 from the previous equation again. So actually there is 2 tasks here. I added another 2. So you will be not boring. You can do something. Okay, let's proceed further. So we are now at another chapter, chapter 3, which is named Viscous Flow in Narrow Ekman Layers and Boundaries. The ambiguous representation of geostrophic flow 14, this one. Oh, I didn't put the number. Let's put. $214, of course. Oh, putting down 214. The ambiguous representation of the geostrophic flow 14 from the previous section 2.3 is actually obtained by discarding in the original equation 2.5 those terms that are extremely small, provided that for this flow the length and time scales are comparable with the characteristic quantities from the section 2.2, the section which previous to this session. In uniquely defined real flow, not only these characteristic scale are present, but also singularity, smallest and smallest scale. Again, I just have to mention that we remove the term which are responsible for viscosity, and those are responsible for inertia. And but in the real situation, of course, the small scales flow, which related to this effect. And first of all, we are studying only Ekman velocity effect, because actually inertia we can completely neglect at this approach. To describe such small-scale flow, it is necessary to take into account the terms proportional to the Ekman number E capital and the Rossby number epsilon, which is in initial equation 2.5, due to the fact that in the small-scale part of the flow, this small number will effectively be divided into small lengths and time scales, which take in the corresponding derivatives. Okay, So this is some general preface to this chapter. Let's start from the particular paragraph of this chapter. In paragraph 1, which name flow and Ekman layers with a negligibly small Rossby number. So we neglect. Now we return somehow the equation. So we neglect by Rossby number term, Rossby number, and all the terms that connecting with Rossby, but keep the viscosity. So we just note that first of all, it is necessary to take into account the viscous term proportional to the Ekman number, capital E, which being in form of the higher derivatives, allow us to satisfy the exact boundary condition of this 6 boundary condition from 2.5 initial system, and thus uniquely determine the flow. It's necessary to stress that the flow which we previously found is not uniquely determined. This is the problem. We can define it in a different way. But to remove this ambiguity, we should go to the account of the viscous force, because it's near the higher order derivatives. In this case, we will first discuss the terms proportional to the Rossby number E epsilon in 2.5. And instead of the first equation in the system, we will have, okay, it's already written here. Now I will repeat it on the board and comment, of course. Let me remove the old stuff. Okay, the main commentary on this reduced system is that, in fact, again, we give rid of the nonlinear term. This is perhaps the most big advantage of the geostrophic approximation. So actually, removing the Rossby term, assuming that the Rossby number is not, help us a lot, because we remove the nonlinearity and we are in the linear system. This linear system is possible to solve much more easily and much more precisely than nonlinear system. But of course, then we have some difficulties now, because equation becomes sufficiently more complicated than it was initially. So this equation look not that complicated. I will write down now it. You will see that it's indeed not so much complicated, and you see it's there. But nevertheless, this system is rather simple in the vector representation. Unfortunately, we cannot solve directly the vector presentation. So eventually, we will expand this system in the corresponding coordinates, in spherical coordinates, of course, because the boundary is on the spherical boundary. And then we can manage to satisfy exact boundary condition, not approximate like we did before, and to match this geostrophic flow, very simple geostrophic flow, to the upper boundary of the viscous layer, and consequently to obtain the right solution, at least at the moment for the Ekman number. So neglecting by the Rossby number, as it's written here, we have this simplified equation. To fit more, I will start it a bit on top. So we just rearrange the term to see them more precisely. So we put the gradient of pressure on the first place. Then we have velocity vector multiplied cross product on the unit z vector or the vertical axis. And all of this is simply equal to the E capital on the Laplacian or nabla squared of the velocity. So this constitutes the very introductory formula to this chapter, 0. The number is 0. It's also necessary to stress that this is not simply squared of nabla function. This is actually, this one is more precisely equal to the double rotor with minus sign. So it's not, indeed not scalar operator, but it's indeed vector operator. It's important to mention. If we say here we just use the this part of this lambda function, lambda operator, and if there is a divergence is not, then there is no any more contribution. But if divergence is plane enforced, then we have to add to this term gradient of the divergence. Something like that. So here we have the divergence, and here the gradient of divergence. Of course, if in our case divergence is not, but in the general case, this Laplacian, of course, in the Cartesian coordinate, it's simply reduced to the scalar operator. So the second derivative of x, second derivative of y, and second derivative of z, sum up of those terms. But it's only in Cartesian coordinate. If we go to any other coordinate system, it will be very much different from the scalar operator. So it's necessary to mention. Yes. And this is thanks to the person who allowed me to understand that, or stress that maybe, understand. So the initial neglecting of the inertia term proportional to the small Rossby number epsilon is justified by the fact that if we, on the contrary, first neglect the viscous terms proportional to the small Ekman number E capital, then it will be imposed to unequally construct the flow with the remaining initial term and satisfy all the boundary condition 2.5. From the asymptotic point of view, this corresponds to the fact that in the problem under consideration, we must first find a solution in the limit of an infinitely small Rossby number. The accuracy of such an asymptotic solution is estimated by the value of the Rossby number, which for the US core corresponds to the value of about 10 to minus 4%. So actually we just symbolically here that removing of the Rossby number is correspond to the accuracy 10 to minus 4%. So it's more than enough accuracy in our case, because usually the most of the estimation are very often just an order of magnitude. So here we are quite safe working in this limit. And of course, omitting all the nonlinear term. The effect at viscous of viscosity should primarily be felt near the spherical boundary of the liquid core of the planet under consideration. Okay. Oh no. Okay. Okay, so it's again the reference on the picture you saw many times. I will not repeat it and find, but nevertheless you see that the configuration of the planetary layer. So therefore the natural coordinate system, again reference for the initial system, with the first equation replaced by this zero equation, with this one, will be a spherical coordinate system. Let us write all this equation and boundary condition in detail for their further use in this section. So let us start with the equation 0. Let's start the equation 0. The spherical component of this equation are determined by the scalar multiplication by the corresponding unit vector. For more details, see problem 3.1 below. Here we also state the problem. As a result, for the three components of equation 0, we obtain the system. Let's comment and write down this general system. As I already told to you, if we proceed to the detailed representation from the vector representation, of course we can get much more lengthy equation, very much more. So we just start from this equation, and pressure is on the first place because it's the most important term, and may be of equal importance or maybe greater even, but at least comparable with the pressure is the Coriolis term. So we start from them. And again, as I already told you, that the Ekman number are in front of the Laplacian, but not ordinary Laplacian, but the vector Laplacian. And it has a very tricky form, especially in the spherical coordinate system. So we just, let's write down and comment every term of this equation. First of all, we, of course, expand P. Here we simply take for the r coordinate, for the spherical radius r, just dp by dr. Then component of the radial, let's stress here that this is gradient r component. So gradient r is the unit radial vector in radial direction, as I like. So then we start with the Coriolis force. It's important to understand that the Coriolis force in the radial direction is corresponding to the velocity component, which is in phi direction. Again, we have this rule of the cross, that for such a complicated term which are coming from the cross product, there is some sort of the cross. So we have the r component, which is going from the v phi direction. So this is the shows the tricky way of the rather tricky way of the Coriolis force, that it's not acting directly, but somehow in the cross it's twist, and actually twist everything. So why we expand it like that? Of course, we use obvious expansion. And then a bit more complicated nature is, of course, we keep E capital, which is the Ekman number. Then we have rather lengthy equation. I don't know if I am here. Okay, but I will try. So, of course, first of all, we have just scalar Laplacian. Let me to stress the difference between scalar and non-scalar. Here put not square of the nabla function, but the just lambda function, just to stress that it's vector. Okay, so but for the first component, of course, we have scalar Laplacian, and for the r. And again, you see that in the case when we effectively have not cross, because we have the double cross actually here, but double cross somehow cancel each other. So after one cross, we have sort of the twisted nature of all the flow, all the everything that appear here. But if we act twice, then crosses somehow cancel each other, and we have a sort of the symmetric nature. So we are actually working on the air component, and the major component is appear here like that, because it's somehow symmetric representation. But of course, there is some traces of the spherical coordinate system. The most simple one is like that. Then there is even contribution of the other component of the velocity, or other component of the velocity, which is constituted in this way. Theta. Here we have a lot of signs. Theta. And finally, of course, we have only also third component. In every component, we have all three of them. But on the top, of course, the component which somehow symmetrical, which is produced from the initial value. And the final azimuthal component here is GVP. Okay, I fit it by dphi. And it's interesting just to stress here that when we involve another component of the velocity, again there is some symmetry. The theta component, we taking the partial derivatives with theta as well. Phi component, we taking the partial derivative with phi. So there is some symmetry everywhere. Let's proceed further to the theta component, which is of course here we have involved with Lamé coefficient, which is for this component is just R. And about the Coriolis force here, we have again okay. Okay, what is written in my notes? But I'm afraid that there is a mistake here. I'm afraid that I'm mistaken because it's repeats that one. Definitely it should be the, as far as I see, perhaps not theta, perhaps R. I don't know. Okay, please check that term. Just expanding by rotor. I'm not sure that it was written correct. But hopefully the rest is correct. So again, we have scalar nabla operator, or double or the nabla squared, and it's again include. First of all, it's include theta component, of course. Then it's include again radial component, because it's even preview for the break this sort of symmetry rule, but maybe not so much. 2 over r square dv d theta d theta. But nevertheless, we have the theta component. It's sort of the mixture. Then we gain theta component like that, and divided by r squared minus theta squared. And finally, we have phi component. To cosine theta r squared sinus squared theta. It's a bit complicated. D v phi d phi. Okay, now we can number this formula. 3.1. Maybe that's correct. Yeah, perhaps it's correct. Maybe I just afraid, but please make sure nevertheless. I think that it's correct, but and the major contribution is actually here. The most important contribution is in the phi direction. And here we have coefficient Lamé r sine theta, so it's walking like that, r sine theta, and dp by dphi. And here we have sort of the major contribution to the Coriolis force, which constitute with two terms. Here we have only one terms for this component, but for the phi component we have two terms in the Coriolis force, which is in the spherical system, and both are quite important. So we have 2 cosine theta v theta, and I just write here to fit it in this place. Then plus 2 sine theta where again we see this cross rule here. We have where and theta and v theta, maybe not so precisely cross rule, but nevertheless here the Coriolis term work like that. And eventually we again have, of course, again we have square on tabla on v phi, and then we have plus theta. Oh, sorry. dvr by d phi and plus 2 cosine theta quadrat sine quadrat theta dv theta by d phi and the final term is just v phi without any derivatives s quadrat Time. Okay, seems I didn't mistake anywhere. Okay, so this is actually the consequences of Navier-Stokes equation, where we neglect by Rossby term or all nonlinear term, and it's in the spherical system. It's quite lengthy. Okay. Okay, so here it's have 2 pages, so you can just write it down if you didn't write something not before that, so you can write it down. Okay, so we need divergence as well, of course. Why not to use the divergence? And necessary to stress that here this Laplacian operator is again in spherical coordinate system. It's not that simple like in the Cartesian coordinate system. So it was to write down all this Laplacian in spherical system coordinate. I mean, but it's not exactly Laplacian for the whole equation. It's only for the part of the Laplacian. It's necessary to stress. But nevertheless, this Laplacian is exactly correspond to the corresponding spherical Laplacian, or maybe more precisely a delta function. So actually, by definition, we have that this expression which used here is by definition just the product of 2 Laplacian. So it becomes scalar product, because actually every nabla is sort of the vector. If we multiply it scalar on itself, it will be scalar. And this scalar is in spherical coordinate system, can be represented. No, it's not shown here. Yeah, it's shown here. Let's write down here, it's at will. One over r square. Again, I stress that here coefficient Lamé is equal unity for the radial component. But when we have double nabla operator, we should operate with remaining Lamé terms. We should multiply them, here multiply and here divide. So eventually we are getting this term like that. It's important that here we have r square, and it's in some solution it becomes rather important. So we have double r operator which work like that. Then we have again coefficient Lamé for this is r, but we should take into account other coefficient of Lamé. And here an important addition, that sign is appear here. And the most maybe simple form is for the phi component. It's just multiplication of the all Lamé coefficient squared. And double derivatives, partial derivatives of phi. Okay, this is another formula, 3.2. Oh, no, it's without numbers, sorry. It's just actually explanational formula, which it's not dissolve the number. Okay, so let's proceed. The real formula and the last formula, which formally constitutes the system of equation for this problem, is of course divergence free, and it's written here. Let's write down and comment it's here as well. So we have again the display with Lamé coefficient, and it's now very similar to that one, you see. We are taking the partial derivatives of r squared VR. And it's interesting that from these derivatives, we have such interesting dependence like proportional to the inverse power of r, which we usually, when we expand the equation. Because basically there are many contributions where we first of all take into account radial component. And for the theta component, of course, we have r sine theta. Again, multiplication of the Lamé coefficient, not square because it's like here, it was here. But the derivative is against sinus theta, very similar one, and also very symmetric because the theta component, we are taking partial derivative as theta as well. And for the same rule is plain for the phi component, azimuthal rotational component. We have an r sin theta, the same as here. And then we have derivatives of v phi over d phi. So this dissolves a special number, 3.2. This is divergence condition written in the spherical system coordinate. So the system of equation 1 and 2, actually this one and this one, is finally closed by the boundary condition from 2.5 from the general system, which in the spherical coordinate system under consideration are described in detail as. There is still some place, hopefully I fit it there. So it's after all this dimensionalization, which we take place here, we have in a rather simple form. So at r equals c, so on the outer actually boundary, which rotate with the mantle in case of the Earth, or maybe to the outer mantle for the other planets, or anyhow to the outer boundary layer. So at r equals c, as again I just mentioned that it's for the Earth case, this c is about 3. So first of all, we have that the radial component of the velocity is not. We already discussed it because it cannot penetrate. Then, because our coordinate system is directly related to this mantle, on the boundary of which we are formulate this boundary condition, so theta component is also not at this point, and also, of course, the phi component is also not, because it should be exactly the same boundary condition as the mantle is rotating in our coordinate system. So the boundary condition is just 0 everywhere. And at the inner boundary, situation is slightly different because we suppose that the inner boundary is rotated with slightly another angular velocity. So of course the first two terms are the same. I just show it like that to make things clear that it's exactly the same. Also, radial component of the velocity 0, theta component of the velocity 0, and here, okay, maybe. Okay, this constitute. Oh, it's even written in Russian. Okay, so at this Russian pre means that at r equals c, and this pre is also at r equals 1. At least have some fun in Russian language. Okay, and the most important component, which actually drive all the solution, that v phi. And because we chose as unity the radius of the inner core, so this v phi is simply sine theta. With this scaling which we adopt before that. So the system is very much simplified. Actually, it's important to note that this system at the moment has only one parameter. So it's just one parameter system, so it's a very big achievement. So this is its own formula, of course. (3.3) very symmetrical formula. While the boundary conditions are quite antisymmetric because there is 0 everywhere on one boundary and there is some differential rotation imposed on another boundary. Okay. Let us quality analyze the obtained system 1, 3 here. 1, 2, 3. So this is complete system, which constitute all the condition, everything. Let us qualitatively analyze the obtained system 1, 3 in order to identify in its small viscous scale that determine the flow near the boundary. To do this, we will select in equation 1 the terms with the inertial Coriolis force and the term with the viscous force. So initial Coriolis force I already told you, this is this term which consists one term. Here there is other term also constitutes the similar term. And there is also maybe the most important one on the phi direction, which consists two terms, Coriolis force. And if we consider in terms of viscous force, this is very length stuff. But here we should take into account the highest derivative, because we suppose that this thing is working in thin layer. So if we divide it on the characteristic thickness of the thin layer, some layers becomes, some the terms becomes more important, and other not so important, because first of all we are looking in the radial direction how it's work. You immediately could see that all these terms which are outside here are not so important like this first, because it constitutes second derivative, and namely in radial direction, which is important near the boundary and make this small very thin boundary layer. And the effectively differentiation is in a radial coordinate system is effective actually in this case in the r direction. So if we take the higher order derivatives, namely in r direction, so frankly speaking, here we have derivatives in another variable, and here we have derivatives. Of course, it's somehow hidden here. It appears from here. Yes, but nevertheless, it's derivatives of the second order in r direction. So many, not simply it's more important. It's many order of importance, because here we have actually derivatives of order of 1, and here this is the order of magnitude of all these derivatives should be divided, should be as we take the small thickness of the layer, divided some one on this small thickness, and then put in square. So it will be very important term if we consider it's radial. But all the other terms are not problem. Let me summarize it somehow. The term describing the Coriolis force are in the left-hand parts of equation 1. I just showed you. And the terms with the hands and are directly proportional to one of the velocity v component. And here to these two components. The terms describing the viscosity are in the right-hand parts and are proportional to extremely small Ekman number. So from one point of view, it's proportional to extremely small number, but from another point of view, it's proportional to the extremely larger term which is connected with the second order derivatives in r direction as in our case. So the term describing the viscosity are in the right-hand part and are proportional to the extremely small Ekman number. Therefore, the corresponding viscous interaction can be neglected, whereas the scale of the flow is comparable to unity. So this is the maybe main message. Whereas the scale of the flow is comparable of the unity, we can use the simple geostrophic approximation, which I showed you in the previous lecture. And here we can neglect by this small Ekman number term. However, therefore, the corresponding viscous interaction can be neglected, again I stress that, whereas the scale of the flow is comparable to unity. The presence of small scales of the flow at the boundary will, first of all, lead to the fact that the square of the small scale, let's note it like, oh no, it's okay. Scale. So let's suppose that the scale is small, and the thickness of this small scale is proportional to the delta. So the corresponding the presence of small scale of the flow at the boundary will first of all lead to the fact that the square of this small scale, theta square, will effectively manifest itself in the denominator of corresponding radial derivatives from Laplacian operator in the right-hand side of 1. So it's the same as I told to you. So if we have delta square, so from this Laplacian operator, especially from this term, we should stress from this term, which is against the radius, it's even becomes theta square. So very roughly, to make some balance, to reach the balance between this Coriolis term and pressure term, of course, and this viscous term, we should very roughly, of course, reach a balance that square of thickness of the boundary layer is about the Ekman number. So in this case, you see that if the thickness of the boundary layer which coming from this place, and you see that here we have the radial derivatives. So this is numbered as formula 1, 3, 4. It's a rather important formula that we balance in the way that to reach this equality. Then you see, if you consider any term of this in order of magnitude, then you see that here we have Ekman number, and here we are divided by delta number. And if they are comparable, so we eventually get in here the term which is constitute like that. We take the epsilon capital, and effectively, when we are taking the radial derivatives, and double radial derivatives actually, we are in effect that delta is squared here. And to reach the balance, actually to reach the balance between this term and this term, we can, of course, the state the same actually as it was stated here, that its value is of order 1. So in some sense, we are getting the qualitative picture how these things are working. So we just see that there is the Ekman number, and to put it in game that allow to coincide with the Coriolis number, with the pressure number term, we should manage with the Zinn boundary layer. And it's this Zinn boundary layer even has its own name, of course, Ekman boundary layer, and due to the person who invented it actually from this consideration. So therefore, the corresponding viscous interaction can be neglected, whereas the scale of the flow is comparable to unity. The presence of small scale of the flow at the boundary will first of all lead to the fact that the square of the small scale manifests itself in the denominator, as already shown in denominator. Here, denominator. Of the corresponding radial derivative from the Laplacian operate in the right-hand side of here, this corresponding Laplacian, and of course we take only the radial component, which is the most important. Accordingly, if we require that the viscous force and Coriolis force balance each other, then we get. Okay, I repeat it second time a little bit in other words, just for you to understand how these things work. Hopefully you understand. So thus, the main asymptotic parameter determining the viscous flow in narrow boundary layers of thickness of the order of will be the square root of the number of delta. And so actually we see that from this relation, of course it's a crude relation, but nevertheless we can for the estimate just write down from this estimation that the delta thickness of the boundary layer is E to which power? Can you say to which power? Half, yeah, exactly. So just 1/2. Yeah. And this is precisely the thickness of the boundary layer. My congratulations. You understand how this thing is working and how this, namely, this 1/2 is appearing. Show that it's working well. Okay. How many time we spent? I didn't count. How many time we spent on this till this moment? Huh? 1 hour already? Oh, okay, let's have a break. Maybe just a small break, yes, Rani? Yeah, small break. I will just sit down for a minute. Okay. Let's conclude the previous chapter. This conclusion is that it's working. Okay. Thus, the main asymptotic parameter determines the viscous flow in narrow boundary layers of thickness of order of this e to the one half will be the square root of the number. So actually, I already wrote this, maybe one of the most important summary of this previous paragraph. Let's now start at this next paragraph in chapter 3, second paragraph, which is named as asymptotic expansion in a root of the Ekman number. So actually we found the small parameter here, and this small parameter, it's necessary to stress that effectively it's not Ekman number, but Ekman number to the half, because namely this small parameter is working on some distance. So we should scale somehow the distance with this parameter, and then to see to which equation it's lead. So we will search a solution in the form. Quite good parameter, why not to use it? Moreover, its problem is very simple in the sense that it actually has only one parameter. So we reduce it, it's a lot. In order to find the type of expansion in terms of a small parameter, it is selected so that the main terms are balanced. This expansion usually has a standard form. So this is quite a standard form. I will write to you. All this small parameter expansion usually work in this standard form. The only not so standard thing here in this expansion that this small parameter is enter near the higher orders derivative. So this, of course, allow us to take it into account and properly to expand every stuff that we have. But nevertheless, to my recollection, pick up the Ekman boundary layer parameter near the higher order derivatives is perhaps the most simple one, because very often if we have small parameter against the higher order derivatives, we not simply use this expansion, but usually in expansion there is some sort of jump term or whatever you name it, like in WKBG solution. All of this stuff will appear later, we'll show it. But in the simplest scale, like a Ekman boundary layer, this expansion is quite simple and it's quite straightforward. Actually, for this somehow singularity system, because it's singular in the sense that there is a very small scale against the ordinary scale, and there are very small scales. So this is sort of the singularity. But this singularity, which is developed for the Ekman boundary layer, perhaps one of the most easily treated singularities. So I will show you right now how it works, but first we will show the expansion, and this expansion I will show you and comment, of course, how it works. After, when I remove all the stuff from the blackboard. Okay. So as a standard approach, we will search a solution in form of the expansion in terms of a small parameter delta equal, sorry. Delta equal square root of Ekman number. This is our small parameter. Just should stress it. parameter. Since this parameter has a clear physical meaning, I'm just repeating, as the thickness of the viscous boundary layer. And so we expand in the standard form using this smallness. And so we expand very simple. We just take velocity field, initial velocity field, then we expand it to the zero order. At zero order, we just suppose that there is 0 at this expansion parameter, and correspondingly V0 approximation. Then the next, in quite similar fashion, we have plus in the first order. Of course, we cannot write that, but nevertheless, just to stress the method, how it works, let's put 1 here. And this, of course, corresponds to V1, vector of V1. And of course, there are another terms, but as far as I told to you that if Ekman number is for real reverse molecular value is 10 to minus 15, then we could neglect very freely the terms of order delta squared, which is in fact is equal, maybe not equal, but in order of magnitude, better to say. That is in order of magnitude as Ekman number. So 10 to minus 15, of course, we can neglect. So for us, it's more than enough, these two terms. And the similar expansion is in pressure, of course. Again, we put zero order pressure here. Then first order approximation here. And plus some value which is of order delta squared. So this constitutes the formula 3.5. So here the order of magnitude and of the delta is square as such a term which are smaller than actually Ekman number, because square of this delta is about the Ekman number. So in order of magnitude to the first term, main term. Such small terms can be confidently neglected, since for the Earth it's at least less than 10 to minus 8. For the Earth it's 10, this Ekman number is less, even 10 to minus 8. But it's for turbulent value, this upper bound. But for it's turbulent. While for the real molecular value, it's 10 to minus 15, as already told. Molecular value. So we are quite safe to remove that. Moreover, in the expansion fire, even terms of order or of delta can be neglected. Moreover, so even this term, which is the first order, of course we can calculate it, but even it has a value, even if we consider turbulent case, it's 10 to minus 4, so even it is not so important. So this is our primary goal, just to find the zero order term, and more precisely to say that it's not zero order, because actually when we operate with this small delta expansion, of course we involve it as the inverse combination in the equation I previously showed to you. So it becomes rather important, and term compared with the other term like a Coriolis and pressure force. So thus to describe the flow, it is quite sufficient for us to find in one which okay, here is one. It was in previous lecture. Okay, but nevertheless, just believe that in one it was such a system. So the main terms of the expansion V naught and P naught, which are of the order of unity, or otherwise, actually, we have this or zero. This is of order unity, of course, and this is namely the term we are looking for. So, and further, we will omit this index 0 everywhere, since we will limit ourselves only to the main terms. If we limit ourselves only to the main term, but it's maybe more than enough, because even in the worst case of the Earth, it's 10 to minus 4 accuracy, more than enough. So it's just very good accuracy. So further, when we consider all this stuff, we will take into account this only first term, and it will be enough for our purposes. And to make this thing simply, we just remove the zero. Subscribe this zero index from here and from here, and work with this field. So since the solution we are looking for must be strongly concentrated at a distance delta in the radial direction near the boundary in the boundary layer, it is quite reasonable to assume that taking the derivatives with respect to the radius increases the determinable function by a value inverse to the small scale. So formally, when we are taking some derivatives of r in r direction, in the boundary layer, of course, near the boundary layer and at the boundary layer itself, so it will be of order of magnitude, of course, roughly of 1 over delta. And this is much more than unity. And it's, of course, compensated to the viscous force. Therefore, it is reasonable to introduce, instead of radial variable, you see that actually we should scale with this delta, which is actually Ekman to the 1/2. Since the solution we are looking for must be strongly concentrated at a small distance delta in the radial direction near the boundaries in the boundary layer, it is quite reasonable to assume that the taking derivatives with respect to radius increases the differentiable function by a value inverse to the small scale, or other words, as I wrote here informally. Therefore, it is reasonable to introduce itself instead of the radial variable, a radial stretched variable, somehow stretched on this all this stuff. So we introduce stretched variable sigma to stretch radial stretched variable in the outer and in a boundary layer, which is in accordance with 4, can be identified as, let's go to the next slide, which can be identified as following. So we see that this is different variable, which we explore near the outer boundary and near the inner boundary. So we just make the indexes here at the outer boundary. By definition, of course, we make this stretched variable like that. So we have radius very close to the radius of the outer boundary, which is 3, as I just remember, in the Earth square. And so we just divided it on the delta. So it's at the outer boundary. At the outer boundary, when module, so there is, in mathematicians there is such a vertical line that means that under condition, something like that. So under condition that R minus C, module of R minus C, is of order of magnitude as delta. So close in the boundary layer. And also we can introduce at the inner layer in the same fashion also sigma now with index I, because this is the inner core. And here obviously we expand it like here. It's necessary to mention that R is coming in the first place. R is coming in the first place because okay, no, doesn't matter. So here we have expansion in this way, but here we have expansion in this way. R minus 1 over the delta, obviously, because the inner radius is here set to 1. So again, the similar condition of existence of this boundary layer is that the module of R minus 1 is of order delta. So this is inside this boundary layer. So it constitutes the formula 3.6. So this is stretched variable, which we put here. And here the external variable theta O has a magnitude of the order of unity. So you just under this condition, under this and this condition, you see that this variable, this stretched variable, becomes of order unity. And here it becomes of order unity when we're in this boundary layer. In the outer boundary layer and the internal stretched variable theta E has a magnitude responsible to that of order 1 in the inner boundary layer. Outside the boundary layer, both of these stretched variables becomes very larger in magnitude, and of course we cannot lose them well outside of the boundary layer, only in the boundary layer. And we now substitute the solution in the form of expansion 5 into 1, 2, and using the stretched variable 6, we isolate the leading terms of the expansion. See the index 0, which we omit actually. So again, just saying that I omit the index 0 because we only the first term taken into account. So near the rigid spherical boundary, or in other words, inside the each Ekman boundary layer. Formally, this is done by equating similar term at the highest power of the asymptotic expansion in formally can be done in the asymptotic expansion with the parameter delta equal square root of Ekman. Consequently, for the leading terms of the system of equation 1, 2, it's difficult to return to this equation, but hopefully you can see on your notes. And so the final result looks like this. The final result is possible to write down. So as first, maybe you remember when I considered this very lengthy equation, I stressed your attention on that only the Laplacian, double Laplacian, no, just Laplacian and the double nabla term is important. And moreover, in this double nabla term, only radial term is important. because all the other terms are vanishing. So eventually we get very simple system for this boundary layer. Here, of course, we have gradient P. Then we have Coriolis force, which is look like that. So this is the vector cross product of the velocity on the unit vector in the direction of axis of rotation, which is has a coordinate z. So this is, of course, doesn't change anything. But very importantly, that on the right-hand side, we have plenty of stuff on the right-hand side, if you remember, especially this very lengthy now double squared nabla term. But only the radial derivative is important in this term. Moreover, the second radial derivative. If you remember, this second radial derivatives appear. There is, of course, the first radial derivatives, but nevertheless, the second order radial derivative overcome everything, and even first order derivatives. So it's still 10 to minus 4 accuracy, and eventually even less if we consider the molecular value 10 to minus 8, 10 to minus 8, 10 to minus 7. Anyhow, it's quite more than enough. So we keep only one term. It's a wonderful message that we have only one term here. And this, see, I didn't mark the indexes here because it's the same for this boundary and for this boundary. So I just put the universal here, but of course it's presumed that it's in fact has index E or O. For different position, of course, for one boundary layer and for another boundary layer. And of course the divergence is equal naught. So it constitutes the system 3.7. So here the stretched variable xi is not indexed because the form of this system of equation 7 remains the same in both the outer and any Ekman boundary layer. Okay, so we finished this paragraph, and then we proceed to the next paragraph of this description of the Ekman layer. And then we have a lot of still things to do, while this formula is very simple. Nevertheless, its manifestation requires some additional efforts. Oh, sorry. Okay. Oh, perhaps I should switch to another PowerPoint presentation. Sorry. Okay. 16. So let's start this next chapter. No, not chapter, paragraph. Chapter is bigger and paragraph is much more smaller. So the geostrophic flow 214, which was shown in the previous chapter, obtained in the previous chapter 2, will obviously satisfy equation 7. So it's interesting that this geostrophic flow is obviously satisfies this equation 7. Through the regular or other geostrophic path and the singular or boundary path in the form. So here the singular path appear anyhow, but maybe in so relatively simple expression. So we can choose the form for the velocity field, which is rather natural here. So we just expand it like v theta. And it's necessary to stress that this v theta component is changed only in direction of theta and xi, this expanded variable, and multiplied it by the unit vector in theta direction, of course, which I wrote down in my lovely form of gradients. And there is, as I already told you, another component of the velocity, because you know that due to the non-penetration condition, we cannot consider here the r component of the velocity, because it should vanish. And in this very small boundary layer, from the r component, we only later involve the derivatives. But if we consider the general representation at the start, this r component is just absent. And there is no r dependence for the theta component, because it's very thin boundary layer, so we should not take into account radial dependence of theta component. And the same trick is for the phi component. This phi component I will write down, it's slightly different from it, just to understand better. Here there is a contribution of some, at the moment, arbitrary function, but we defined it later, which depend only, again, not depend on the radius, but depend on this stretched variable. And all this. Then we have this geostrophic flow in order to satisfy the geostrophic solution. And as was already we told and showed to you, that this depends only on cylindrical radius. And the spherical coordinate system, this cylindrical radius is r sine theta. So we just close that and put here the unit vector in the direction of phi. So it's constitute formula 3.8. And it's necessary to stress that here u from S, this S actually, this is cylindrical radius, S. U from S is the derivative of the free pressure function divided in 214. So if you remember that everything was defined via the pressure. So for geostrophic flow, and as already told, this S is actually r sine theta. So this r sine theta is the distance from the rotational axis of the cylindrical radius, or otherwise cylindrical radius. The pure single function u and v theta, this pure singular function u and c theta, why they are singular? Because they involve this stretched variable. So this stretched variable, and this is the sort of the singular function, which concentrated in the boundary layer. But outside the boundary layer, it just vanished, and very quickly. So they should be significant only in the narrow viscous layer near the boundary. Outside this layer, the singular function should decrease so much that neglecting the viscous component in 7 and completely switching to a purely geostrophic flow US. So it's not the accident that we chose this function in this way. So you see that if it's going much less than C, this radial, so it's become negative and just tend to the very small value and eventually vanished and rest only on this geostrophic flow. And the similar situation is for the boundary which is here. So, of course, we from the singular velocity from 8, this singular velocity from the formula 8, it is sufficient to consider both angular component of the vector equation from 7 and 1. From 7 and 1, it was the initial system, actually. Taking into account the geostrophic equation, so of course we also will take into account the geostrophic equation. I will not repeat it, but nevertheless we should meant that again I stress that if we are outside the boundary layer, we remove all this boundary layer solution, but and formation, and the geostrophic flow remains, which depend only on the cylindrical radius. So to obtain the equation, determine the singularity velocity from 8, it is sufficient to consider both angular component of the vector equation from 7 and 1, taking into account the geostrophic equation and the fact that the angular part of the singular pressure gradient is negligibly small. It's important here it's also to stress that not only R component is small in the boundary layer, but also the derivatives which are not radial derivatives of the pressure, they are also small, because you know that when we are taking the derivatives against the radial spherical radius, especially in the boundary layer, then we have the small value divided on the, effectively we divide the change of the pressure on some small value. So the radial component of the pressure, I mean radial in common sense, because pressure is actually gradient of P. And so the radial part of this gradient is important, but the other is not important at all. We can neglect them everywhere